Going on now to the highlights of Chapter 4, going to the vocabulary check. Systems of linear equations. A solution. Consistent. Independent. Dependent. Inconsistent. Substitution. And addition. So I see there are only 7 answers, but one has 2. Okay, there we go, because there are 8 words. In a system of linear equations in 2 variables, if the graph of the equations are the same, the equations are which one here? Well, because the equations are the same, I think we're looking at the word here that they are dependent. Two or more linear equations are called systems, or a system of linear equations. A system of equations that has at least one solution is called, and I recall just doing these the other day in class, consistent. Number 4, what of a system of 2 equations if 2 variables in an ordered pair of numbers, that is a solution for both equations in the system? Well, I think they're using the word solution here, although it's given right there. Again, we may have to go back on that. Number 5. 2 algebraic methods of solving systems of equations are. Now, I don't see graphing here. That would be one. But the ones we were mentioning are substitution and addition. And I guess the key word there, algebraic methods. Okay. Graphing is not an algebraic method, although we use algebra to solve for y and things like that. Okay, number 6, a system of equations that has no solution. That would be inconsistent, and those would be lines that are parallel, and those graphs would be independent, which I believe is our next answer. In a system of linear equations in 2 variables, if the graphs of the equations are different, the equations are called independent, as they would be in the other 2. Okay, so vocabulary helps us communicate. Every definition might be slightly different, and I have learned my definitions a long time ago, so I'm not sticking to the book 100%, but the concept is there. All right, so let's move on. We're going on now to the actual highlights as we review. And the first thing they want us to look at is a set of ordered pairs a solution for this system of equations? And how do we do it? Well, we substitute, in this case, the x, wherever the x is, in each of the equations and the y, and see if we end up with true statements. If you get a true statement, then it is a solution. Okay, and we said the first method we use, bringing material from Chapter 3 into Chapter 4 was being able to graph these linear equations in two variables. And we had a number of techniques. One technique you may recall was to, if it, like it went back here to the wrong page, but here we are. If we had an equation that was in standard form, we might have used the X and Y intercept t-chart, or we could solve the equation for Y and put it in slope-intercept form. And then we would plot our y-intercept and we would plot our slope. And again, we're looking for points of intersection, in this case, a unique one, which is 1, 3. This would be a solution for both of these equations. And the method we're using here is graphing. So in a sense, we're solving these equations simultaneously. And here's where they review the vocabulary with us. And this is something I used in previous videos as well, that if we plot one line and we get, let's say, this line here, and we plot the other graph and we get this line there, and they intersect, those are called a consistent system, that it has at least one solution. And since the equations are different, the equations are independent. Here, even though they may not have looked the same, when we do graph them, one line is on top of the other. So again, with at least one solution, it's consistent. And since they're the same lines, they are dependent. And remember, there's an infinite number of solutions. And then in another case, if there were two graphs, but they are parallel, that is, they have the same slope, but different y-intercepts, there would be no solution. So these are inconsistent and different equations, they are independent. Then we went on to show you algebraically how to solve by not using graphing, but by using algebra, where in this first case they're illustrating substitution. So here x is given as y plus 3. So where the x is in the other equation, you put your y plus 3 there. Now it has an equation with only one variable letter in it. So you solve that as we did in chapter 2, and you get y is 2. Well, if y is 2, you just put the 2 where the y is. 2 minus 3 is a -1. Then your x is a -1, and you have your ordered pair. And you can check it the way we've done it before to see if it is in fact true. Because it's sort of easy to get the wrong sign if you're not careful. Okay, another method we said was the addition method, where as you look at one graph, and the key is have it in standard form, and you might say, well, what can I do since nothing, if we add them together, would cancel out? Well, we have to take this first equation and multiply it by a -3 right there. So each term in the first equation, we're going to multiply by a -3. And every term, this side and that side. And then now notice your -3 and a +3 cancel out. We add up the rest and we get this. Now, once we know that y is a -4, we put it in one of the equations. It doesn't make any difference which one we do, but we're using this first equation here. Where there was a y there, we now put a -4. This becomes a +8. We subtract 8 from both sides, we get x equals 0. Now don't get confused if you get one of the coordinates as equal 0. That's fine. 0 is a good coordinate. It's if you end up with something like 3 equals 4. One of the things we'll look at here, this is not a true statement. If while you're doing your calculations, you get something like this, then the lines are going to be parallel. There's going to be no solution. Or if you end up with something like 4 equals 4, which is a true statement, this would be a condition in which they are actually the same equations, and there would be an infinite number of solutions. So these are things you're going to be looking at, and I'm assuming they're going to give us some of this as we go along here. And here is one right here. So we use substitution here. We're going to put our 3y minus 1 where x is, right there. And know what happens. You get -2 equals -2. Is that a true statement? Yes. Well, these are actually the same equations, but modified in terms of algebra. And when you write the answer, it's usually written in set builder notation. X comma y is such that you write one of the equations. And that's what they're illustrating it here. Okay? Now in this next section, we didn't do 3 variables. So I'm not going to illustrate this for you, but basically it's the same as what we've done. You start with 3 variables, you try to reduce it to 2 by eliminating some, and then eventually you have 2 variables. Again, you want to eliminate another by either addition or substitution until finally you start breaking it and you solve for one, then substitute, solve for the other, and then finally the third. And that's what they're illustrating it here. But we didn't feature that in our course. So we went on to looking then at word problems, and we featured this before, where you read it and reread it, then translate it into algebra, solve it, and then interpret. Does it make sense? Okay? Well, the others were long. This is going to be at 14 minutes. So good luck as you prepare for your final exam.